Hey everyone, welcome to the first video of the channel. And as I said in the introduction video, we're going to be talking a lot about maths, right? And to talk about maths, we need to understand the first thing we have to understand is arithmetics, because arithmetics is the area of math that represents, that studies, that makes relations between numbers. That's how we start making operations, right? These relationships between numbers are called operations. And we have to understand, the first thing we have to understand is that all arithmetical operations derive from addition, right? This might not be entirely true. I'm not sure if that is entirely true, but I was taught that way, and seeing all mathematical operations as variations of addition have made it much easier for me to understand how they actually work, okay? And it also helps you make a better linkage between operations. So, what is addition, right? Addition is the operation we have when we have two numbers and we want to know what total number they represent, right? So if I have 5 and I want to add 5, I will have 10, right? And even though I don't really like this example because it is pretty flawed, a visual way to... There's a car passing. Sorry about that. A visual way to understand how this works is if I have 5 points, I hope you can, if I have 5 points and I want to have more 5 points, if I count those points, I will see that in total I have actually 10 points. Okay, they're arranged in a different way, but there are 10 points here. And it's very interesting to understand this in this way, even though later when I talk about numbers, we will see that numbers aren't a real thing. They aren't material things. They don't really exist. They are abstractions. But that's a subject for another video. For today's video, this is as far as we need to understand, right? Now, I've said that all operations derive from addition, and we're gonna get there. But what I meant by that is that subtraction, multiplication, division, exponentiation, rooting, they all derive from addition. We can understand all of them if we understand addition, right? Now, before we get further into this, I want to dive a little deeper into how addition works, because not everybody understands the actual process of making more complex additions. Operations with one order numbers, so with only one digit numbers, they are a lot easier than we have, let's say, 4, 8, 6, 9 plus 3, 8, 5. Okay? Now, a lot of people know how to solve this. If you put this on paper, it is really easy to solve this. But I want to understand the logics behind it, right? Also, in the video about numbers, we will see about orders and classes, but let's see them in practice, okay? So we know that orders are separated like this. Here we have 3 orders, which are the units, the dozens, the hundreds. Here's the order of the thousands, the units of thousands. I believe that's how it's called in English. If this is wrong, I will put some text on the screen because I'm not quite sure how it's translated to English, but in Portuguese it would be something like that. So, and here we will have a class. Here we would have another class which is incomplete because it only gets to the 4, only to the units of thousands. But what I want to understand here is when, or better, why do we start addition, making this kind of operation from the smallest number to the biggest number? And the reason why we do this is because if we start from the smallest number, we can be sure that that value will not be changed later, okay? So, if I have here 5 plus 9, this is going to be 14, right? And in 14, what we can observe is that it has 2 orders, right? There's a unit and there's a dozen, right? And again, here we have units and dozens. And because 14 is a number that it's now representing this part, I think you can see that it's representing this part of the operation. When we add it to the operation here, when we count this, when we add this, we have to put 14 as 4 here and 1 here, right? This is 14 being included in that. Now, answering the question that I made a little earlier, the reason why we start from the smallest one and not from 4, for example, is because if we started from the biggest number, we can risk having it being changed later, right? Because numbers can only increase from right to left, okay? So all numbers, when we're talking about orders, they increase from right to left. So units, when summed, they can reach a number that goes beyond the units order, right? But when we have dozens being summed, they cannot they can't go back, they can decrease to the units, okay? So we can be sure that if I'm dealing with dozens, I will not be changing the units. But if I'm changing the units, I might run the risk of changing the dozens, okay? And we don't really have to finish that because this is just the idea that I wanted to pass. And now that we have that in mind, how addition works in a deeper level than just solving it, we can now understand how subtraction works based on addition, right? Now, it might seem a bit obvious for everybody who already understands math in a more advanced way. For people who are already in college, for example, this is going to might look a little over too simple, but not everyone understands how this process works. So we can have here 10 plus 5, okay? And this is equal to 15, okay? Now we can have also 10 minus 5, and this is going to be 5, okay? But another way to reach this, another way to represent this whole thing would be to have 10 plus minus 5, which would also be equal to 5. Okay, so all subtraction can be represented through addition. And some people might ask, well, but you're subtracting it here. I'm not subtracting it. I'm adding a negative number, which is a different, but at the same time, equal thing to subtracting it. Okay? Because for a more visual example, let's say I have 10 here, I have 5 here, I'll have 5 here, minus 5 here, and minus 10 here. If I have 10 right here, and I include this part of the, I believe it's called the numeric line. I hope it's called the numeric line in English. I add this part here. This is going to be the very opposite of this, okay? So 5 and minus 5, they're opposites. So they cancel themselves, okay? So they find each other, they cancel themselves, they together reach 0, right? And if I'm counting from here, I have minus 5, I can go all the way to 0. Sorry, no, that's a poor way to explain it. A better way would be, imagine I'm canceling this out, okay? If I am canceling this out because minus 5 and 5 are equal to 0, all that's left for me is this part, which is equal to 5, okay? Because, well, if we have 5 and we add 5, we have 10. I hope that's not too confusing, but that is just a demonstration of how subtraction is equivalent to equation to addition. And of course we can have operations such as, let's say, 10 plus minus 100, right? Which would be minus 90. We could, for a better understanding, this could also be minus 100 plus 10, right? And back to the numerical line, we can easily imagine that, well, I'm negative on 90. So if I add a positive 10, I'm negative on 100. And if I add a positive 10, I will be negative on just 90. Okay? So subtraction is a variation of addition. Now, multiplication, I think this one is the easiest to understand, is also a variation of addition. But how exactly? Again, with the example of 5, let's say we have 5 times, oh my god, that's really ugly. We have 5 times 5. What I'm saying here is that I have the number 5 added to himself 5 times. Okay? Yeah, 5. And if I have 5 with 5, I have 10. Here's 10. And here says 5. I have 10 with 10, which is equal to 20. Which goes to 20. And 20 plus 5 is 25. And here we know that 5 times 5 is equal to 25. So multiplication, it's a more advanced, if I can put it like that, form of addition. But it's still addition, right? What I want to know with multiplication is, what I have with multiplication is I am adding this number 5 to itself 5 times, okay? And because I'm repeating the same number, this might look a little confusing, but we can have 13 times 3, okay? Let's say 14, just to make this a little more different. I have 14 times 3, which is the same thing as 14 plus 14 plus 14, right? And I have 4, 8, 12. So again, with addition, I start with the units, so I know I have 12, right? And 10 plus 10 plus 10 is equal to 30, right? So 30, I won't change the units because 0 is equal to nothing, so 2. Yeah, that's correct. I was a bit confused for a second, but this is equal to 42. Okay, this is a very good visual of how multiplication works through addition. Now, subtraction, it is easier to understand through, division. Division is easier to be understood through subtraction, right? So I will first explain it through subtraction to then explain it through addition. So let's say I have, to make this very easy, 100 divided by 10. So what I want to find here, the x I want to find, is the number that multiplied by 10 is going to give me 100. And okay, we all know that this is 10. But through subtraction, what we can imagine is how many times we have x times that we can subtract 10 from 100. So if we were to count 100 minus 10 minus 10 minus 10 until, well, 1, 2, 3, 4. We will have, this is just to say that we have 5 number subtractions to 10 here. We will have in total, we will be subtracting 10 from 100 10 times until we reach 0. So this is a good form of understanding how this works. And just to make the calculation a little more visual, let's put 50 here. And now I can more easily do it. I would have 50 minus 10 minus 10 minus 10 minus 10 minus 10. Yeah, which would be equal to 0. And this means that this is equal to 50. I have 5 times the number 10 here. I am subtracting the number 10 5 times from 50. Okay? So 5 is a number that will go here because I can remove 10 from 50 5 times till I reach 0. Okay? Now, through addition, what we could observe is that this also means that I can have 50 plus minus 10 plus minus 10 plus minus 10 plus minus 10, 1, 2, 4, plus minus 10, which would also be equal to 0. Okay? So I have again the opposite of 10 being added 5 times. And this again would tell me that I can add the opposite of 10 to 50 5 times. It's another way to represent it. And this shows how division can be expressed and understood through addition. Okay, now I've covered addition, multiplication, now exponentiation. This one is a little bit more complex, but it can also be understood. We're going to first understand exponentiation through multiplication and then through addition, right? So let's say that I have the number 3 to the power of 2, 3 squared. We know that this is equal to 3 times 3, right? Which is equal to 9. Now, we have seen that a way to represent multiplication, what we are doing in multiplication is we're adding this number to itself this many times. So what we're doing here is we have 3 plus 3 plus 3. We have the number 3 being added, being summed, being added 3 times, which is equal to 9, right? So we can understand this in this way. We could have also 5, no, I've been using a lot of 5. Let's say I have 7 squared, okay, which is equal to 7 times 7, which is equal to 49, right? Again, this can be understood through multiplication, and multiplication can be understood through addition. So 7 plus 7 plus 7 plus 7 plus 7 plus 7 plus 7, which if we were to do this, we would see that it's equal to 49, okay? So this is how exponentiation is also understood through addition. Exponentiation is also a variation of addition. And the same is valid for rooting. The same is valid for rooting. So if I have the square root of 25, okay, what I want to, let me just put this here to be more clear. What I want to know is which number x to the power of 2, just like here, is equal to 25. And we know that this is 5. We know that x in this case is 5. So a way to represent this through multiplication would be to say that x times x is equal to 25. Okay? So, which is also to say that x added to itself, x times, would be equal to 25. So if we have an x number of x, we have 25. Okay? And this is not to say that we can solve square rooting this way, but it is how it might be represented through addition, right? So let me just put this up here. So I have this. We know that the square root of 25 is 5. So 5 to the power of 2 is equal to 25, which is equal to 5 times 5, which is still equal to 25, which is equal to 5 plus 5 plus 5 plus 5 plus 5, which is still equal to 25. Okay? And this is just to say that the square root of 25 is 5. Okay? I do hope my explanation is not too confusing, and I hope I'm not using the wrong terms. If anyone could correct me if I'm wrong in some term in the comments, I would be really grateful, because as I mentioned in the introduction video, English is not my first language. I'm not used to explaining mathematics in English. I usually teach this in Portuguese. But here's again how we can see that rooting can be expressed as addition, right? But why am I discussing why addition is the fundamental, it's the base of arithmetic, which is the base of mathematics? Because if we understand how a concept works at its simplest level, at its base, at its core, in the most simplistic way, we can understand it better, right? We don't have to do such a mental effort to do it. So you can understand that 5 plus 5 plus 5 is equal to 15, right? This is very easy to do, right? A child, a child could solve this very easily, right? But maybe not all children would be able to solve 5 times 3, right? Which is still equal to 25. Okay, let me put it as 5 times 3, which is equal to 25. Not all children would be able to see this. I'm sorry, to 15, not 25. To 15. Not all children would be able to solve this, but they would be able to do this, right? So if we can understand this more complex concept through a simplest one, through a simpler one, we can, of course, understand it better. Okay? I hope I have been clear in my explanation. This is all I have for today. I hope you have enjoyed this video. If there are any suggestions of topics for me to talk about, if there are any suggestions on how to improve my videos, I am very open to hear them. And well, that is it for today. I hope I have been useful, and I'll see you all on the next video.